Welcome back, design junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Glad to be here for this one. It's going to be a heavy one.
Oh, absolutely. Usually when we talk about a medical diagnosis, there's this expectation of precision, right? You break your arm, the x-ray shows that jagged white line, and a doctor just points and says, there it is.
Yeah, it's binary. Like it's either broken or it's not.
Exactly. You look at the film and the problem is just perfectly visible.
We inherently crave that kind of categorization, I think, just because it's comforting.
Right. But then you step into the world of actual physical thermal fluid system design, and suddenly that x-ray machine is just, well, it's completely useless. We are looking at an engineering landscape that is, honestly, it's murky.
It is incredibly murky.
Because on paper, everything looks pristine. Your spreadsheet gives you a precise efficiency number down to, like, the 4th decimal place. But in reality, fluid flow and heat transfer are chaotic. They're highly sensitive to boundary conditions, and they almost never behave the way a simplified 1D textbook equation suggests.
Yeah, it's the absolute definition of diagnostic muddy waters.
Yeah.
The gap between theoretical thermodynamic elegance and actual, operational machinery is where most critical engineering failures happen.
Exactly. And that is the mission of today's deep dive. We are taking a dense, heavy look at the source material spanning thermodynamics, fluid mechanics, and turbomachinery, and we are extracting the practical, real-world constraints you actually need to know.
Which is so needed because people get lost in the theory.
Right, because today is all about mechanical engineering made simple. We are breaking down the biggest pain points and real-world issues engineers keep running into with thermal fluid system design.
We really need to call out the common misconceptions that just keep screwing designs up.
Oh, big time. We're talking about massive systemic traps like designing heat engines for pure theoretical efficiency instead of maximum usable power. Or ignoring the incredibly messy three-dimensional reality of airflow inside a spinning compressor.
It's terrifying how often that happens.
So true. Then we are going to walk through a step-by-step approach so you don't fall into these same traps, starting from base thermodynamic properties and moving all the way up to optimizing complex turbomachinery in practice.
It's a journey for sure.
Okay, let's unpack this. Have you ever wondered why the beautiful, perfectly efficient thermodynamic cycles you learned about in school completely fail to produce usable power in the real world?
Oh, man, it is the ultimate rude awakening for a young engineer. You spent years in school calculating the Carnot cycle, right? Which is the theoretical gold standard for thermodynamic efficiency.
The absolute peak.
Exactly. And the Carnot efficiency is famously simple. It is 1 minus the ratio of the cold reservoir temperature to the hot reservoir temperature. Mathematically, it is beautiful.
It really is.
It represents a perfectly reversible engine where absolutely no energy is wasted to friction, to turbulence, or to, uncontrolled heat transfer.
And this is huge. Reversible is the trap word there.
Yes.
For a process to be truly perfectly reversible in thermodynamics, there can't be any driving forces that create entropy. Which means to transfer heat from a hot reservoir into your working fluid without any thermodynamic loss, the temperature difference between the reservoir and the fluid must be exactly 0.
Precisely. And if the temperature difference is 0, the heat transfer rate is 0.
Right.
To have absolutely 0 thermal gradient and 0 friction, you need infinite time to transfer the heat from the hot reservoir to the working fluid, and then, infinite time to reject it to the cold reservoir.
Which means your actual energy flow rate is 0.
Exactly 0.
And since power is just energy transferred per unit of time, your actual power output is literally 0.
Yeah, it's a harsh reality.
It's like designing a hyper-aerodynamic car that gets 10,000 miles to the gallon. But it only achieves that efficiency if you drive it at 0.001 miles per hour.
That's a great analogy.
Right, like you might have record-breaking efficiency, but if you need to actually deliver a payload across the country, your real-world productivity is entirely useless.
That is the exact reality. Think about a steady flow engine, something like a massive steam turbine in a power plant or a closed-cycle gas turbine. To get actual measurable shaft work out of that engine, you must overcome the physical thermal resistances between the heat reservoirs and your working fluid.
Because the metal itself is in the way.
Right. The metal walls of the boiler and the condenser present a barrier. Heat only flows across that barrier when there is a meaningful temperature difference. But the moment you introduce that temperature difference to force the heat through, you introduce irreversibility. You immediately lose that perfect Carnot efficiency.
Wait, so if we actually push for maximum efficiency, we literally get zero power out of it.
Literally zero.
So you are forced to make a compromise. You deliberately sacrifice some of that perfect theoretical efficiency because you have to move the heat fast enough to generate actual megawatts of power.
Yes. And the math provides a specific optimal point for that compromise. If your goal is to get the maximum power output, not the maximum efficiency, but the absolute most work done per second, the optimal temperature ratio across the engine shifts dramatically.
How so?
It dictates that the optimal temperature ratio happens when the internal ratio equals the square root of the cold reservoir temperature divided by the hot reservoir temperature, or, Tc over Th to the power of 1/2.
Okay, let me make sure I'm visualizing the physics of this correctly. Instead of just using the raw external temperatures of the environment, say the burning hole and the cold river water, we have to look at the temperature of the working fluid inside the engine's heat exchangers as it absorbs and rejects that heat.
Correct. Let's look at a concrete example from the sources to ground this. Imagine a heat engine connected to a scorching hot reservoir at 1600 Kelvin and rejecting heat to a cold reservoir at 400 Kelvin.
Okay, 1600 and 400.
Right. If you are chasing maximum Carnot efficiency, you would theoretically design the engine's internal working fluid to match those external temperatures exactly. 1600 on the hot side, 400 on the cold side.
But again, with no temperature delta across the heat exchanger walls, no heat actually flows. You get a perfect spreadsheet and a dead engine.
Exactly. So we apply the physical optimization for maximum power. We take the ratio of the cold to hot reservoirs. 400 divided by 1600, which is 1/4, or 0.25.
Right.
The square root of 0.25 is 0.5. This geometric mean dictates exactly how we set our internal operating temperatures. To maximize the energy flow rate through the engine, the working fluid needs to operate at drastically different temperatures than the surrounding reservoirs to physically force that heat transfer through the metal.
How do engineers balance this in the real world without just arbitrarily guessing where to set the operating temperatures? You obviously don't want a machine that burns through fuel terribly inefficiently, but you also need it to keep the lights on in a city.
What's fascinating here is that internally reversible engines operating at maximum power output naturally settle at a practical efficiency that perfectly balances the Carnot ideal with the physical reality of thermal resistances.
Oh, wow.
Yeah. When you calculate the engine's efficiency at that maximum power point, it is significantly lower than the Carnot ideal, but it represents the absolute peak of what you can achieve while actually extracting the maximum amount of useful work per second.
It changes the entire design paradigm.
Completely. You stop chasing a theoretical ghost and start designing for the maximum rate of energy transfer.
That completely flips the script. You aren't just trying to aggressively conserve every single joule of energy. You're trying to move those joules as effectively as possible to generate horsepower. But to calculate any of these power outputs in the real world, to figure out how much work you can actually extract across a turbine, you need to know the state of your working fluid. You need to know its internal energy, its enthalpy, and its entropy.
And that brings us to one of the biggest foundational hurdles in thermal fluid design, the measurement problem.
Oh, this is a big one.
It is. You can easily install a thermocouple into a pipe to measure temperature. You can attach a gauge to measure pressure. You can measure the physical volume of a containment vessel. Pressure, specific volume, and temperature, P, V, and T. These are tangible macro-scale properties.
Right, you can physically see the dial move.
Exactly. But you cannot go to an industrial supplier and purchase an entropy meter.
Right. I can't just stick a probe into a high-pressure steam line and have a digital readout tell me the internal energy or the entropy. They are unmeasurable in a direct physical sense. So how do engineers bypass this? How do we not get completely stalled trying to measure the unmeasurable chaos of the fluid?
We rely on the mathematics of continuous surfaces, specifically the Maxwell relations.
Ah, okay.
These are fundamental mathematical properties that allow engineers to relate changes in unmeasurable properties, like entropy, directly to changes in the properties we can easily measure, like pressure, volume, and temperature.
I want to break this down because mathematics of continuous surfaces sounds incredibly abstract. Let's ground this.
Sure.
If I have a single component system, like pure water or pure nitrogen, the relationship between all its thermodynamic properties forms a three-dimensional surface, right? Imagine a 3D graph. The x-axis is entropy, the axis is specific volume, and the vertical z-axis is the specific internal energy.
Yes, and because the state of that pure fluid is smooth and continuous, assuming we aren't crossing a phase boundary yet. That 3D surface has to be mathematically continuous. And a continuous mathematical surface has a very strict rule. The cross derivatives must be equal.
Meaning, it's like hiking a perfectly smooth mountain. It doesn't matter if I walk north then east or east then north. The ultimate slope and elevation I reach at a specific GPS coordinate on that mountain is identical regardless of the path I took to get to that point.
Precisely. And from that mathematical absolute of the mountain slope, we derive the Maxwell relations.
Okay, give me an example of one.
For example, one of the foundational relations states that the partial derivative of entropy with respect to specific volume at constant temperature is exactly equal to the partial derivative of pressure with respect to temperature at constant volume.
Let me translate that into physical hardware because that is a massive conceptual leap. The left side of that equation is about entropy, the unmeasurable chaos, the dispersion of energy as the volume changes. I can't measure that.
Right, you can't buy a gauge for it.
But the right side, the change in pressure when you change the temperature inside a rigid, constant volume tank, I can absolutely measure that. I just need a steel box, a pressure gauge, a thermometer, and a Bunsen burner.
Exactly. The Maxwell relations act as the Rosetta Stone of thermodynamics. They allow you to calculate precisely how much the unmeasurable entropy changes by simply recording how the physical pressure responds to a temperature shift on a gauge in a lab.
That's brilliant.
It turns abstract physics into measurable, actionable engineering data.
So we completely bypass the need for an entropy meter. We just track the pressure gauge on the outside of the rigid tank, and the math bridges the gap. That is an incredibly elegant workaround.
It really is.
But we also have to deal with specific heat capacities, the exact amount of thermal energy it takes to raise the temperature of the fluid, and there is a very strict, unforgiving rule about the specific heat at constant pressure, which we call CP, versus the specific heat at constant volume, CV.
Yes. The math, supported by these same partial derivatives, dictates that the specific heat at constant pressure, CEP, must always be mathematically greater than or equal to the specific heat at constant volume, CV.
And physically, that makes sense. If I heat a gas inside a rigid steel tank, which is constant volume, all the heat goes purely into raising the temperature of the gas.
Correct.
But if I heat that same gas in a cylinder with a movable piston, so constant pressure, the gas expands as it heats up. It has to push the piston against the weight of the atmosphere. It has to do physical work.
Exactly. It's pushing back against the environment.
So I need to add more total heat to achieve the same temperature rise because some of that heat is being spent moving the piston, therefore CP is greater.
That is the macroscopic physical view, and it is entirely correct. But the underlying mathematical reason goes even deeper, and it involves another partial derivative.
Neutral one.
It involves the rate of change of pressure with respect to specific volume at a constant temperature. This specific derivative must always be negative.
Wait, why is that so crucial? What happens if that derivative isn't negative?
Think about what a positive value would mean physically. If the rate of change of pressure with respect to volume were positive, it would mean that as you squeeze a substance, as you decrease its physical volume, its internal pressure would also decrease.
That sounds bizarre.
Or conversely, if you pull on it and increase its volume, its internal pressure would spontaneously increase.
That sounds like an absolute nightmare. If I squeeze a balloon, it naturally pushes back harder against my hands. The pressure goes up as the volume goes down. That's a negative relationship.
Exactly.
If it were positive, applying even a tiny amount of pressure to the outside of the balloon would cause the pressure inside to drop, meaning the atmosphere would crush it even faster, lowering the internal pressure further.
Causing it to shrink more until it completely collapsed out of existence in a spontaneous microsecond.
Wow.
Yeah. If a substance had a positive derivative there, it would be fundamentally structurally unstable. The mathematical reality that CP must be greater than or equal to CV is tied directly to the fact that matter, as we know it, inherently resists being compressed.
It literally saves us from the physical universe just spontaneously collapsing in on itself. It's wild how a simple mathematical derivative dictates the structural stability of reality.
It's the hidden scaffolding of the universe.
But as we mentioned earlier, these smooth, continuous surfaces only apply when the fluid is well behaved. We don't always deal with nice, continuous states. Sometimes the fluid boils. Sometimes liquid water violently flashes into high-pressure steam. That is a massive discontinuity. The mountain suddenly has a sheer cliff face.
Phase changes are where engineering gets incredibly dangerous. When water boils into steam, it expands violently.
Right.
If we didn't have a way to mathematically model that exact transition, Our safety pressure relief valves, our industrial boilers, and our nuclear reactor containment vessels would be designed based on complete guesswork.
And a guessing game with high-pressure steam usually ends with a crater where your facility used to be.
Correct.
So how do we handle the mathematics of that sheer cliff face?
Through the Clausius-Clapeyron equation.
Yeah.
When a fluid changes phase, say, from liquid water to vapor, it happens at a constant pressure and a constant temperature. We call those the saturation values.
Okay.
During that exact phase change, the fluid absorbs a massive amount of thermal energy, which we call the latent heat of vaporization. It absorbs all this energy without changing its temperature at all.
Right. A pot of boiling water stays at exactly 100 degrees Celsius.
Mhm.
You can crank the burner as high as you want, but the liquid won't get hotter. It will just convert into steam faster.
Using the exact same continuous surface math from the Maxwell relations, the Clausius-Clapeyron equation proves that this massive, invisible latent heat of vaporization is directly tied to the physical slope of the saturation line on a simple pressure-temperature diagram.
Wait, just the slope.
Just the slope. By taking a fluid in a lab and simply measuring how its boiling point changes as you increase the pressure, which is literally just plotting a curve on a graph, you can calculate exactly how much energy is required to tear the liquid molecules apart into a gas.
That's crazy.
You don't need to measure the intermolecular bonds. You just need to know the slope of the boiling curve.
It's another brilliant shortcut. We've mathematically defined the fluid's behavior. We know how to extract maximum power. We know how to calculate its unmeasurable thermodynamic properties using simple lab gauges. And we know exactly how much energy it absorbs when it boils.
Which is a huge toolbox.
But a fluid just sitting stationary in a tank isn't doing much useful work for us. To be a functioning machine, we have to move it. We have to force it through pipes, drive it down cooling channels, and blast it over microchips. And that brings us to a massive chronic pain point for thermal fluid engineers.
Internal flow. The physical reality of forcing a viscous fluid through a highly confined space.
I cannot tell you how many design spreadsheets and preliminary CFD models I've seen where the engineer just assumes the fluid is perfectly behaved from the very millimeter it enters the pipe.
Too many. Far too many.
They assume the flow is instantly fully developed right at the inlet. But treating the entrance of a pipe like the middle of a pipe is a dangerous misconception. The flow entrance region behaves completely differently, and ignoring it leads to massive catastrophic miscalculations in both pressure drop and heat transfer.
It is an incredibly common trap because fully developed flow is mathematically easy to solve. But think about the physical reality. When fluid first enters a pipe from a large reservoir, the velocity profile is basically uniform. It's moving at the exact same speed all across the cross-section.
Right.
But immediately, the very first layer of fluid touching the metal wall stops moving entirely due to friction. We call this the no-slip condition. Because fluids have viscosity internal friction, this stationary layer slows down the next layer, which slows down the next layer.
It cascades.
Exactly. This creates a boundary layer of slow-moving fluid that grows thicker and thicker as the flow moves further down the pipe.
The easiest way to visualize this is a traffic jam. If you have a highway where everyone is doing 60 miles per hour, but suddenly a car breaks down on the right shoulder, the cars in the right lane have to slow down. Then the cars in the middle lane have to hit their brakes to merge, and slowly, that pocket of slow-moving traffic expands from the wall out into the center lanes of the highway.
That's a perfect analogy. Because the fluid near the walls is drastically slowing down, the fluid in the exact center of the pipe actually has to speed up to compensate. It has to accelerate to maintain the same overall mass flow rate through the pipe.
That makes sense.
This entire region, where the boundary layer is growing and the core is accelerating, is the hydrodynamic entrance region. Only after these boundary layers grow so thick that they meet perfectly in the center of the pipe does the flow become fully developed, settling into that classic unchanging parabolic velocity profile known as Hagen-Poiseuille flow.
So the critical question is, how long does that take? How far down the pipe does this traffic jam extend? Because if I'm designing a compact heat exchanger with very short pipes, my fluid might never actually reach that fully developed parabolic state.
The scaling for this flow entrance length is well documented in the sources. For laminar flow, the physical distance it takes to become fully developed is roughly 10 to the power of -2 times the Reynolds number times the diameter.
And since a high Reynolds number means the fluid has high inertial forces, it's either moving very fast or it has very low viscosity, like a thin gas. A highly turbulent, fast-moving flow is going to stretch that entrance region incredibly far down the pipe.
Precisely. And in that entrance region, The physical friction against the wall is significantly higher than in the fully developed region,
Why is that?
because the boundary layer is very thin at the entrance, which means the velocity gradient, the difference in speed between the stationary wall and the fast-moving core, is incredibly steep. If you calculate the pressure drop required for your pump, assuming a nice, easy, fully developed flow, but your actual physical system is comprised of short pipes that are entirely in the entrance region, your friction calculations will be way off.
So your pump will be vastly undersized.
Entirely undersized.
You'll build the physical prototype, turn the pump on, and a trickle will come out the other end because the friction choked it to death. But it's not just about the pressure drop, is it? It's also about thermal management. Just like there is a velocity boundary layer, there is a thermal entrance length as well.
Yes. Just as the friction from the wall slowly creeps into the center of the pipe, if the wall is at a different temperature than the fluid, a thermal boundary layer grows. Heat slowly diffuses from the wall into the core of the fluid. And the length of this thermal entrance region depends heavily on a specific fluid property, the Prandtl number.
The Prandtl number. It's the ratio of molecular momentum diffusivity to thermal diffusivity. In simple terms, it describes how fast physical momentum spreads through the fluid compared to how fast heat spreads through it.
Exactly. For a fluid like heavy engine oil, which has a massive Prandtl number, momentum spreads much faster than heat. The fluid is highly viscous, but poorly conductive. So the velocity profile might become fully developed relatively quickly, but the temperature profile takes a huge physical distance to develop. The thermal entrance length is incredibly long.
I did.
And here's the trap. The heat transfer coefficient in this thermal entrance region is extremely high right at the inlet where the boundary layer is paper thin, but it decays exponentially as the flow moves downstream and the boundary layer thickens.
So if I design a cooling channel, assuming a uniform, fully developed heat transfer coefficient across the whole length, my design is going to be wildly inaccurate. The front of the channel will overcool, and the back of the channel will literally melt.
That is exactly what happens in poorly designed electronics cooling.
Here's where it gets really interesting, because we aren't just talking about long, generic water pipes anymore. We are talking about microchannels cooling the latest, most powerful, incredibly dense computer chips in massive, hyperscale server farms. You don't just arbitrarily guess a channel width anymore. We actually have a specific step-by-step approach to optimize these channel sizes for cooling electronics.
You absolutely cannot afford to guess when you have millions of dollars of silicon crammed into a tiny rack space, generating the heat of a small oven. The engineering goal here is to maximize the heat transfer density, figuring out exactly how much heat you can remove from a highly constrained, specific physical volume.
Right.
And the absolute key to this optimization is a dimensionless parameter called the Bijan number.
Let's define the physics of that. The Bijan number mathematically captures the specified pressure drop across the channel, so delta, P times L squared, divided by the fluid's dynamic viscosity, mu, times its thermal diffusivity, alpha.
The true beauty of the Bijan number is that it perfectly encapsulates the exact physical constraints of a real-world electronics cooling problem. You have a strictly fixed volume for your heatsink, a fixed length of the fins, and a highly specific limited pressure drop that your small onboard cooling fan can provide. You can't just put a bigger fan on it. You are completely constrained.
So, given those rigid constraints, how does this step-by-step optimization work in practice?
You analyze the two extreme physical asymptotes of the design. Let's say you're designing a stack of parallel plates, your classic aluminum heatsink fins. If you make the spacing between the plates extremely large, you can only physically fit a few plates in your given volume.
Makes sense.
Now, the fan easily pushes the air through, very low friction, but your total metal surface area available for heat transfer is incredibly small. The thermal resistance is too high, the air doesn't pick up enough heat, and the electronic components completely overheat.
Okay, so the large spacing asymptote is a failure due to lack of surface area. What if I go the other way? What if I pack them in really, really tight, thousands of paper-thin fins to maximize surface area?
If the spacing is too small, the internal friction becomes immense. The pressure drop required to force air through those microscopic gaps is drastically higher than what your small cooling fan can actually deliver. The fluid essentially chokes. It can't flow. It stagnates between the fins.
Oh, wow.
And once again, the whole volume overheats, this time due to lack of airflow.
So you have a large spacing failure and a small spacing failure. The optimal physical design has to be the exact intersection of those two extremes.
That is the exact mathematical approach. The optimal spacing for parallel plates is found exactly where these two asymptotes cross. The math gives the exact optimal geometry. It states that the ratio of the optimal spacing dopt to the length of the channel, L, is approximately 2.7 times the Bijon number to the power of -1/4.
That's incredibly specific.
It is. Specifically, as your allowable pressure drop increases, meaning you have a stronger fan, the optimal spacing gets tighter.
Let's visualize this inside that massive server farm, rack after rack of buzzing circuit boards. The computing power of that room is strictly limited by how fast you can remove the heat. By using this exact Bijon number methodology, you maximize the heat transfer density. You tune the spacing of the fins perfectly so that the thermal boundary layers growing off of adjacent fins just barely meet exactly at the exit plane of the channel.
That is the crucial underlying physical insight. Think about what happens if you get the spacing wrong. If the boundary layers meet too early near the inlet, you have fully developed flow for the rest of the channel, which means the heat transfer coefficient drops and becomes highly inefficient. Conversely, if the fins are too far apart and the boundary layers never meet, you have a massive channel of wasted space in the center between the plates, where cold air is just bypassing the hot metal entirely without picking up any heat. The absolute mathematically optimal design occurs when the thermal boundary layers merge just as the fluid leaves the heat sink.
That is so deeply satisfying from a design perspective. It means that every single cubic millimeter of air pushed by that fan is working as hard as possible to absorb heat right up until the exact moment it exhausts out the back. If you nail that Bijon number optimization, you can pack drastically more computing power into the exact same physical server chassis without melting the chips.
If we connect this to the bigger picture, this geometric optimization principle isn't just a clever trick for parallel plates. It is a universal physical truth. The exact same methodology intersecting the asymptotes of extreme physical geometries based on the Bijon or Rayleigh numbers is used to optimize natural convection cooling, forced turbulent duct flow, complex arrays of staggered plates, and even bundles of cooling cylinders.
It scales to everything.
It is a fundamental law of allocating flow architecture in a confined volume.
But what happens when the fluid isn't confined inside a channel? We've perfectly optimized our internal flows, but what happens when the fluid flows over the outside of our components? Say, an exposed sensor on an aircraft or a standalone component in a wind tunnel. That takes us out of the constrained pipe and into the open ocean, so to speak.
External force convection. It is an entirely different fluid dynamic beast. When an object is in a free stream, the boundary layer is no longer constrained by a physical wall on the other side. It can grow, it can evolve, and crucially, if the pressure conditions are wrong, it can separate entirely from the object.
The mechanics of external flow cover flow over flat plates, cylinders, and spheres. And the common thread tying all of this together is the boundary layer battlefield. It dictates absolutely everything. The friction drag pulling on the object, the heat transfer cooling the object, and the pressure drag behind the object.
And solving the mathematical equations for these external boundary layers is notoriously, punishingly difficult. The Navier-Stokes equations, which govern the conservation of mass, momentum, and energy in a fluid, are highly nonlinear partial differential equations. To actually solve them without a supercomputer, classical engineers had to use a brilliant mathematical trick called the similarity transformation technique.
This is where we take a 2D problem and collapse it. We combine the x and y spatial dependence, the distance along the plate and the distance away from the plate, into a single independent variable, usually called eta. Why does this physical hack allow the math to work?
Because it turns an unsolvable partial differential equation into a solvable ordinary differential equation. Think about it physically. If you take a snapshot of the velocity profile inside the boundary layer 1 inch down the flat plate, and then take another snapshot 10 inches down the plate, the boundary layer is much thicker. But the fundamental shape of the curve looks geometrically identical if you just scale up the zoom.
Oh, I see.
Because nature scales perfectly here, engineers can collapse two messy spatial dimensions into one single mathematical variable. It takes an impossible 2D calculus nightmare and turns it into a solvable line graph. By using that single variable eta, we can find an exact analytical solution for the velocity and temperature fields over a flat plate.
But a perfectly flat plate aligned perfectly with the wind is the easiest possible scenario. Real engineering is messy. The airflow hits things at angles. This leads to Faulkner scan flow past a wedge. Why do we care about a wedge shape?
Because a wedge fundamentally introduces a pressure gradient. As fluid approaches a wedge, the free stream velocity changes depending on the angle of that wedge. If the fluid is being squeezed and forced to speed up, which we call a favorable pressure gradient, the boundary layer is physically pushed down against the surface. It stays thin, tightly attached, and heat transfer is excellent.
Okay, that sounds ideal.
But if the fluid is moving past the wedge and beginning to slow down, an adverse pressure gradient, the pressure is actually pushing back against the flow.
And when the pressure pushes back against a slow-moving boundary layer that is already losing energy to friction, the fluid literally stops, turns around, and separates from the surface entirely.
Exactly. And flow separation is the absolute enemy of thermal fluid design. It creates a massive turbulent wake, it skyrockets your pressure drag, and it completely destroys your predictable heat transfer. The Faulkner scan solutions mathematically prove how fundamentally the heat transfer off a solid surface shifts depending on whether that pressure gradient is helping you or fighting you.
Let's bring this abstract wedge physics directly back to a real-world electronics cooling issue. Plate fin versus pin fin heat sinks. We just spent all this time perfectly optimizing the spacing of parallel plate fins using the Bijon number. We nailed the design. But then reality throws a massive curveball.
It does. As modern electronic systems become increasingly compact, think about the inside of a high-end laptop or a densely packed server blade, the path for the cooling airflow gets severely constrained. You can absolutely no longer guarantee a nice, clean, perfectly straight airflow from your fan to your heatsink.
Because there's just too much stuff in the way.
Right. The air is violently bouncing off other components, turning sharp corners, and hitting the heatsink from completely unpredictable shifting directions.
And plate fin heat sinks, the ones we just optimized, degrade incredibly rapidly if the air doesn't hit them perfectly straight on. If the air comes in even at a slight angle, it hits the broad side of the very first fin, the flow separates massively, it creates a huge turbulent wake, and the rest of the carefully spaced channel is entirely starved of cooling air. Your Bijon number optimization is ruined because the air bypasses the channel.
The physical solution to this unpredictable, chaotic airflow is the pin-fin heatsink. Instead of long, continuous aluminum plates, you machine a forest of small, vertical, cylindrical pins. Pin fins are physically robust against the direction of the airflow.
Because they're round.
Exactly. Because they are cylinders, it doesn't matter what angle the air approaches from. The cross-flow dynamics remain generally the same. The air will weave its way through the forest of pins and continue to extract heat regardless of the approach angle.
There is a very common, highly optimized physical setup for this. Placing a small axial fan directly above a pin-fin heatsink blowing straight down onto the chip.
This is a brilliant use of external flow geometry. The air from the fan blows straight down. Initially, it flows longitudinally down the central pins, which behaves almost exactly like flow along a flat plate.
Okay.
But then, because it physically hits the solid baseboard attached to the hot microchip, it has to abruptly turn 90 degrees. It then transitions into crossflow, moving horizontally across the outer perimeter pins before finally exhausting out the open sides of the heatsink.
It's like a dual-action cooler. It leverages both internal parallel flow characteristics in the center and external cross-flow characteristics on the edges. But wait, if pin fins are so adaptable and they completely solve the problem of unpredictable flow direction, why don't we just use them for absolutely everything? Why do plate fins even still exist?
As always in mechanical engineering, you cannot escape the harsh physical trade-offs. Pin fins have massive drawbacks. First, simple manufacturing complexity. Extruding a massive long piece of aluminum with straight plate fins is incredibly cheap and fast. You just push metal through a die.
Yeah, that makes sense.
But machining, forging, or casting thousands of tiny, perfectly spaced cylindrical pins is a slow, expensive manufacturing process.
Right, the cost scales up quickly. But what about the fluid dynamics? There has to be a physical penalty, too.
The penalty is the pressure drop. While pin fins offer fantastic heat transfer, especially because they generate constant turbulent wake zones that mix the fluid, the aerodynamic drag coefficient of a bluff cylinder in crossflow is extremely high, compared to the sleek profile of a flat plate perfectly aligned with the flow.
So it's harder to push the air through.
Much harder. You pay a massive penalty in pressure drop. It requires a much stronger, louder, much more power-hungry fan to physically force the air through a dense pin-fin array. You only spend that money and that fan power when the unpredictable flow direction makes plate fins physically unviable.
It's always a balancing act. Heat transfer versus pumping power. Manufacturing costs versus thermal performance. We've talked extensively about cooling stationary objects, servers, microchips, flat plates. Now, let's ramp up the complexity and look at the ultimate mechanical engineering challenge. Moving the fluid itself with massive rotating blades.
Turbomachinery. where absolutely all of the simple 1D rules become significantly more complicated and, honestly, dangerous.
We are diving into axial flow compressors and fans.
Huh?
Think of the giant spinning titanium blades at the front of a commercial jet engine or a massive industrial ventilation fan in a mine shaft. The biggest misconception here, the absolute trap that ruins amateur designs, is treating the flow as purely two-dimensional and entirely ignoring radial equilibrium.
When you look at a cross-section of a compressor blade drawn on a piece of paper or in a simple CAD model, it's very easy to just assume the air moves straight through horizontally from the front to the back in a nice, clean, two-dimensional plane.
Ah,
But physical reality is 3D.
Right.
You have a fluid moving through an annular duct, a giant donut-shaped ring between the central hub and the outer casing. And that fluid is swirling violently because the blades are spinning at thousands of RPM.
And swirling fluid means centrifugal force. The air has mass and it's spinning. It physically wants to get flung outward toward the outer casing, exactly like you get pushed hard against the door of a car when the driver takes a sharp turn at high speed.
Exactly. To physically prevent all the air from piling up against the outer wall and starving the inner hub, there must be a balance of forces. This is the radial equilibrium equation.
Okay, what does that balance look like?
There absolutely must be a radial pressure gradient specifically, a higher static pressure at the outer casing and a lower static pressure at the inner hub to balance the centrifugal forces of the swirling fluid pushing outward. If you ignore this pressure gradient in your design, your air won't go where your spreadsheet thinks it will, the flow will completely separate from the blades, and your compressor will catastrophically fail.
This brings us to a classic design approach called free vortex flow. So if I'm designing a compressor, my math looks incredibly clean if I specifically design the twist of my blade to create a free vortex swirl distribution. Because if I do that, the math magically guarantees that the axial velocity, the speed the air moves straight through the engine from front to back, remains perfectly constant from the inner hub all the way to the outer dip.
It was highly attractive to early aviation designers because it is mathematically elegant. If the axial velocity is constant across the entire radius, you can essentially design the compressor stage as if it were a simple 2D cascade. It makes the spreadsheet math incredibly easy to solve.
But practically, doesn't that mean I have to force the blade to do extreme things to make that constant velocity a reality? Don't I have to twist the blade at massive angles near the hub?
Exactly, and that extreme twist is where the physical reality shatters the mathematical elegance. To achieve that constant axial velocity, the free vortex design physically forces the fluid to deflect at extreme, almost impossible angles near the inner wall, the hub. The blades have to be highly twisted, which causes the flow to separate, creating a massive stall zone right at the root of the blade.
And it gets worse at the outside edge, right? Because the tip of the blade is spinning physically faster than the root.
Yes. Conversely, near the outer wall, the tip casing, the free vortex design forces the flow into dangerously high velocities, easily pushing it into high Mach numbers.
So to make my spreadsheet clean and my math easy, I've physically created supersonic shock waves tearing off the tip of my blades, creating massive drag and noise, and I've created a dead stall zone at the root of my blades.
Precisely. It is a perfect historical example of theoretical mathematical elegance causing absolute practical failure in hardware. Modern jet engine designers have to move completely away from strict free vortex flow. They intentionally design for non-constant axial velocity just to physically manage those Mach numbers at the tip and prevent flow separation at the root, even if it makes the 3D radial equilibrium math exponentially harder to solve.
And the math gets even harder when the compressor isn't running at its perfectly designed, laboratory-tested speed, because no machine operates perfectly at its single design point.
No engine operates at its exact design point 100% of the time. You have to start it up from zero, you have to throttle it down, you have to respond to turbulent air conditions. The key parameter engineers use to manage this is the stage loading factor, denoted by the Greek letter Ci. It's a measure of exactly how much thermodynamic work each single stage of the compressor is physically doing on the air.
And this loading factor is strongly tied to the flow coefficient, phi, which essentially represents the physical mass flow rate of the air moving axially through the engine.
There is a truly fascinating counterintuitive insight from experimental compressor cascade data regarding this. If you have a heavily loaded stage, where the stage loading factor, Cψ, is very high, approaching 1, it is actually the most flexible and robust design off design. It physically produces very little variation in performance, even when the mass flow of the air changes significantly.
Wait, really? You'd intuitively think a compressor stage working at its absolute maximum thermodynamic limit would be fragile, on the edge of failure, and prone to breaking down if the wind changes even slightly.
It is entirely counterintuitive. But the physical physics of the velocity triangles prove it. It's actually the lightly loaded stages, where psi is very low, doing very little work per stage, that are highly sensitive and fragile.
Why is that?
In a lightly loaded stage, even a tiny change in the physical mass flow rate causes massive disproportionate changes in the relative flow angles. The air suddenly hits the physical metal blades at the completely wrong angle of attack. The boundary layer violently separates, and it leads directly to stall and catastrophic compressor surge.
Let's visualize this with a commercial jet engine. Say you design an engine purely for cruising altitude. That's your pristine design point. The air is thin, the speed is constant. It's a perfectly controlled environment. If you decide to use lightly loaded stages to maximize your aerodynamic efficiency at that specific point, you get great gas mileage at 30,000 feet. But what happens on the runway?
When that jet is taking off, when the air at sea level is incredibly dense, the pilot is throttling the engine up to maximum power, and the mass flow is completely different from the cruise condition. Those lightly loaded stages will be pushed incredibly far off their design point. The flow angles will shift wildly, the boundary layers will detach from those long blades, and the engine could stall violently, losing all thrust right when the aircraft needs maximum power to leave the ground. The design fails because you haven't accounted for the off-design flow coefficient shifts.
This raises an important question. How do modern engineers actually handle this in the real world? If free vortex math is flawed and lightly loaded stages are dangerously sensitive and the 3D radial equilibrium math is a nightmare, how do we actually build functioning jet engines?
They rely on incredibly complex computational time marching methods. They use powerful CFD software to simulate the flow. The computation physically starts from an assumed guessed flow field, and the governing Navier-Stokes equations are mathematically marched forward in time, step by step, until they reach a steady, converged physical solution. It can handle local supersonic patches, shock waves, and incredibly complex 3D secondary flows that manual math could never touch.
But you cannot just blindly trust the software.
Absolutely not. And this is the most critical takeaway for any thermal fluid engineer. If you do not intimately understand the base physics we just discussed, the radial equilibrium forcing air at the casing, the boundary layer separation on a wedge, and the extreme danger of lightly loaded stages, you will just suffer from garbage in, garbage out software errors.
The software will just lie to you beautifully.
Exactly. The CFD software will happily output a beautiful, colorful, completely physically impossible 3D model. The software is merely a tool. The human engineer must fundamentally understand the physical reality it is attempting to simulate.
We've covered a massive amount of physical ground today. We started at the absolute base with the Carnot cycle, realizing that maximum theoretical efficiency physically guarantees zero power output. We bypassed the impossibility of measuring entropy by using the Maxwell relations to measure pressure instead. We optimized server farm cooling channels by finding the exact physical intersection of pressure drop and boundary layer growth using the Bijon number. We navigated the chaotic external boundary layers using pin fins, and we just survived the 3D swirling, shockwave-inducing nightmare of turbomachinery. Let's pull this all together by answering the specific, painful questions you, the listener, are likely screaming at your dashboard right now.
It is always essential to connect this high-level theory directly back to the daily physical frustrations engineers face at their CAD stations.
Exactly. I'm going to rapid fire the most common painful questions engineers ask about these topics, and let's apply this exact deep dive directly to their daily work. Question number 1, dealing with internal flow. Why does my physical heat sink prototype perform drastically, measurably worse in the lab testing than my simple design spreadsheet calculated it would?
This is the absolute classic entrance region and bypass failure. Your spreadsheet failed because you likely used a fully developed Nusselt number correlation, assuming perfect, unchanging heat transfer, for a physical flow that is actually still entirely trapped in the entrance region. If your physical heat sink is short, the thermal boundary layer never fully develops, and your average heat transfer is entirely different from what you calculated.
And what about the physical spacing?
That's the other part. You almost certainly didn't physically account for flow bypass. As we proved with the Bijon number optimization, channel spacing is the critical physical constraint. If your fins are packed too tightly to maximize surface area, the internal friction, the pressure drop, is too high for your fan. The air will absolutely not force its way through your perfectly calculated, highly restrictive fins, It will obey the laws of physics, take the path of least resistance, and simply flow around the outside of your heatsink entirely.
The air just dodges it.
Yep, your spreadsheet assumed the mass flow had to go through the fins. The physical reality of fluid dynamics proved otherwise.
A tough, expensive lesson in physics, always taking the easy way out. All right, question 2. Diving into the terrifying world of turbomachinery. Why do my physical compressor blades keep stalling and surging when I simply throttle down the mass flow?
You are physically hitting the surge line on your compressor's performance map. When you reduce the mass flow in the throttle valve, but you maintain a constant rotational speed of the spinning blades, you are directly and drastically dropping your physical flow coefficient. As we explored in the off-design performance physics, this drop in mass flow radically alters the relative flow angles of the air hitting the moving blade.
So it hits at the wrong angle.
Exactly. The air is now physically approaching the leading edge of the blades at far too steep of an angle of attack. The boundary layer simply cannot navigate that sharp turn and remain attached. The fluid violently separates from the low-pressure suction side of the blade, creating a dead wake zone, and you get a local blade stall.
And if that cascade fails?
If this happens across enough blades simultaneously, the entire compressor loses its ability to hold back the high pressure downstream. The high-pressure air violently reverses direction, blasting backward out the front of the engine, which is a compressor surge, and it can physically tear the engine off its mounts.
Wow. Okay, final question. Question 3. Dealing with external flow and boundary layers. How do I physically deal with turbulent flow over rough surfaces? If my manufactured part has a high surface roughness, does it completely ruin my aerodynamic heat transfer?
Not necessarily. In fact, depending on your physical goals, a rough surface might be exactly what you want for heat transfer, but you have to pay the toll in power. Physical surface roughness actually acts to trip the boundary layer. It forces the smooth laminar flow to break down into chaotic turbulence much earlier along the plate, and it physically thickens the turbulent sublayer near the wall.
Okay, so it gets messy fast.
Yes. This increases the local skin friction coefficient, meaning the physical drag pulling on the object skyrockets. But, through what is mathematically known as the Reynolds analogy, a direct physical increase in skin friction corresponds directly to an increase in the heat transfer, specifically the dimensionless Stanton number.
Wait, so making the metal physically rougher actually cools the component better?
Yes. The physical roughness violently churns the turbulent Prandtl number in the sublayer, promoting massive physical mixing and aggressively ripping heat away from the hot wall faster than a smooth, insulating laminar layer ever could. It is a harsh physical trade-off. You get significantly better, more aggressive cooling, but you pay a massive penalty in pressure drop, aerodynamic drag, and the required fan power to overcome that artificially increased friction.
It all comes completely back to that physical balance. Heat transfer versus pumping power. Theoretical efficiency versus actual usable power output.
Before we wrap up, I want to leave you with something to really chew on that builds on exactly everything we've discussed today. We've talked extensively about optimizing fixed physical channel spacing using the Bijan number for static electronics cooling, finding that perfect unchanging geometry where the physical asymptotes cross. But what if future mechanical designs weren't physically static?
What do you mean, like physically shape-shifting heat sinks inside a computer?
Exactly. Imagine a mechanical system with shape-shifting responsive cooling channels. A physical system that biomimics biological vascular systems, exactly like the capillaries in your own body. Channels that dynamically physically expand and contract in real time to maintain the perfect, optimal, local Bijan number as the heat load fluctuates across a microchip.
That sounds like science fiction.
It does, but think about it. If one core of a processor suddenly runs incredibly hot, the microchannels directly over it physically dilate to increase local mass flow, while simultaneously constricting over cooler areas to save fan power. That physically dynamic, constantly adapting architecture is the absolute next frontier of thermal fluid design.
So what does this all mean? It means that whether you are mathematically calculating unmeasurable entropy to find your physical maximum power limit, designing a titanium jet engine compressor that won't violently stall on a dense sea-level takeoff, or trying to pack just one more physical microchip into a server farm without melting the silicon. Relying on simplified, pristine 1D textbook assumptions will completely trap you. You have to design for the messy, three-dimensional, highly chaotic, off-design physical reality. The X-ray machine might be broken, but with the right mathematical relationships and a deep, uncompromising physical intuition, you can still figure out exactly what's going on inside the machine. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.